So now we really get into the fun part. What I hope you can do is this is a great time to even take a break if you've just been sort of plowing through these videos one after the other, because there's, like I said, a lot of information here, and sometimes it can be a little bit overwhelming. So this is a good time to give your brain a little bit of a rest. I would say the next section is like the biggest one that we're going to discuss here, where we start doing what are called operations on sets. Um, and the way that you kind of can think about this is um, just like we add and subtract numbers, right? Those are operations that we perform on numbers, where we take a number and then we add it to another number and we get a new number, right? Or we take a number and subtract a number and we get a new number. Sets can work the same way. We can do operations on sets, and it's kind of like adding or subtracting them. So let's get started. Let's get started. So this is called doing operations on sets. And I'll just start by giving you the two primary names of this to start. We're going to talk about what are called intersections, intersections of sets, and we're also going to talk about what are called unions of sets. So intersections and unions. So an intersection of a set is really the part where it's where the elements that both sets have in common, right? So the intersection of two sets contains the elements that both sets have in common. Okay, so this would be contains the elements that both sets have in common. Um, let's say we have two sets, A and B. It would be the elements that are in both A and B. If you think about the characteristics of those sets, the things that are in the intersection would have to have the characteristics of both of those sets. Maybe you can even think back to Venn diagrams we did earlier in previous videos and remember things that are maybe in the middle parts of those circles. The symbol for an intersection is this sort of upside down U. And so if we're trying to represent the common elements between sets A and B, we write A, then that upside down B and or U, and then B. This means A intersect B. Okay, it's the intersection of A and B. So let's practice this. What I want you to do is make another Venn diagram, draw your two little circles, and I'm going to do that too. I'm going to try to do a better one than I did earlier. I'm going to do a little copy and paste of my what I have here. So I'm going to make a Venn diagram. Let's enlarge it. Okay. We'll come back and we'll do the unions in a little bit. We're going to start with the intersections. Okay, and so we're going to look at a couple different sets. We're going to say the universal set. So the universal set is going to be the whole numbers from 1 to 10. Whole numbers 1 to 10. Okay, and I should even put a rectangle around my Venn diagram. Okay, so the universal set is the whole numbers 1 to 10. We will say set E is the even numbers. And we'll say set T is numbers that are multiples of 3. Okay, so set E is the even numbers and T is multiples of 3. So I'm going to say that this is set E and this is set T. So what I want you to find is E intersect T, or this is what we will find together. Now, if you want to try this, if you think you've got it already, pause and see if you can do it on your own. I'm going to keep going. So what we'll do is we have to just first place the numbers 1 through 10 appropriately in our diagram. So we're going to just go count starting from 1. So 1 belongs outside because it's neither even nor a multiple of 3. 2 belongs here. 3 belongs here. 4 belongs here. 5 belongs here. It's not even. It's not a multiple of 3. 6 is even, and it's a multiple of 3. 7 is out here. 8 here. 9 here. And 10 here. Okay, just examine that for a second. Examine our Venn diagram. What do we notice? Well, we have several numbers that are part of the universal set, but they're outside. We have several numbers that are in the even category, a couple that are in the 3, but then we have one single number in this overlap area. It's the number 6. Intersections of sets are here, right? It's only where those two sets intersect, right? So the number 6 has characteristics of both the even numbers, E, and the multiples of 3, T. So we say that this is its own new little set. E intersect T is equal to the number 6. That is it, okay? E intersect T is the number 6. So what I'd like you to do now is get out your attributes, okay? Get out your attributes, and you're going to pause and do this little activity on your own. And you are going to define set S as the small pieces and set B as the blue pieces. And again, use the physical representations so you can kind of see where all of these things are going to exist, okay? Draw your Venn diagram, lay them out on the paper, set S as the small pieces, set B as the blue pieces, and your job is to find this, all right? So go ahead and pause and then come back to the video. I'll keep going. So if you took all of your attribute pieces and laid them out like we did to start this whole chapter, what you would see is that they would look like this based on how we defined those two sets. Again, set S is the small pieces. So all of your small pieces are going over here on the left. All of your blue pieces are going over here on the right. Notice how we have, again, set S, set B. You got some pieces that are outside. They're in the universal set because they're part of your attributes. They just don't belong in either circle. And what we were finding was S intersect B. We were trying to find just the things that exist in the middle here. And what do we end up with? 4 different elements. 4 different elements. So the way that we would write that is S intersect B is equal to, we would put our brace, and then we would list them. And again, we gave these names. They're listed right on the individual attributes. We would say SBS, right? Small blue square is one element. SBT, small blue triangle, is another. SBH, small blue hexagon, and SBC. And then we would close that brace. There is our answer, right? That's how we list out all of the elements in that new set, S intersect B. All right. So to continue this idea, what we're going to do is we're going to look at a couple different ideas, still using the idea of attributes. I suggest, again, that you play with these physically, but then what we're going to do is shade them. So I'm going to do one example for you, and then I'm going to try to have you do it on a couple on your own. And so what we're going to do is find the intersection of each pair of these different types of attribute pieces. So number one is L intersect H. We're going to find the intersection of L intersect H, which basically means large. They are large for L and hexagons for the H. So they are large pieces and they are hexagons, okay? But then what we're going to do is we're just going to do a little sketch of what our Venn diagram might look like, sort of a simple sketch, and we're going to shade in the area that represents what we're looking for, okay? So if you arranged out all of these pieces, what you would end up with, kind of like before, is a set of all your large pieces and a set of all your hexagons. And there would be some pieces that existed in here. And so we would shade that part of our drawing. Again, you would have some pieces kind of everywhere in this diagram, but this is where those pieces would exist, okay? And so this is what these representative diagrams can look like, okay, without all of the individual attribute pieces shown. So this is what I want you to do for the next two, okay? So number two is ST intersect SC. ST is small triangles, and SC is small circles. Okay, so can you sketch a little diagram that looks like that? And then the third one we'll do is SS, and I'll even put a Q for square, so we know that's small squares, intersect S. And S all by itself is just going to represent small pieces. So this is going to be the intersection between all small squares and all small pieces. So see if you can do, pause the video now and make a little sketch for both of these that looks like this one. I'll keep going. Okay, so for number two, and maybe you used your individual attributes to sketch this out. If so, that's great. What you maybe found when you sketched your diagram was that there were no common elements between small circles and small triangles. And so the circles themselves are completely separate. Small triangles would go here, small circles would go there, and nothing actually would be shaded because they had no common elements. So one thing you can say is that if we actually go back up to this first one, I didn't do this before, but if you did list them out, L intersect H would be equal to large blue hexagon, large red hexagon, and large yellow hexagon. For number two, ST intersect SC would be equal to what? They have no common elements. So what do we say? That's the empty set, which we can represent like that. Do you remember another term for elements that have nothing in common? We say that these two sets, ST and SC, are disjoint. They are disjoint. What do you come up with for this one? We are looking for SQ intersect S. When you sketch this out, what you probably found was that if all your small pieces are inside that circle, all of your small squares are a subset of S. They all exist in here. So that's where the two would intersect. All of the small squares would be the intersection point. In fact, SQ intersect S is really just equal to SQ because SSQ is a subset of S. All right, so that's this idea of intersections. Do you remember the name of the other type of operation that we do? It was called a union. So we're going to kind of go back in those same previous examples in a way, but now we're going to look at it in terms of what we call a union. A union of two sets contains all of the elements of both sets. All of the other elements of both sets. In a Venn diagram, it's kind of like combining the two sets together, right? If you have them overlapped like this, it's not just going to be here, it's going to be here and here as well, okay? A key word when you're doing unions is or, right? The union of two sets A and B is the elements that are either in A or B, or in both of them, okay? Again, the characteristics describing either of the sets must be true for elements in the union. It doesn't have to have the elements of both. It just has to have the elements of, or the characteristics of, either. The symbol for a union is a nice U. That one's easy to remember. So if we say the union of A and B, we write A union B, like that. There's our notation for a union. So we're going to do the same thing we did before. We're going to make a Venn diagram, and let's do it here, just like I did before. Make a Venn diagram with two circles. I think I can sketch that fairly neatly. And the universal set, again, like before, is the whole numbers 1 to 10. And set E is the evens. And set T is the multiples of 3. What we're going to do now is we're going to find E union T. Previously, we did E intersect T. Now we're going to do E union T. Again, pause and try this on your own if you think you've already kind of got an idea. I'll keep going. So before we labeled this as even, this as multiple of 3, and then we started listing the numbers. So just like before, 1 goes here, 2 goes here, 3 goes here, 4 is here, 5 is outside the circles, 6 is in the middle, 7 is here, 8 is here, 9 is over here, and 10 is an even. So when we are finding a union, again, it's not just where they intersect, it's everything included in both sets. So we're really shading, if we're going to shade, we're shading everything in E and everything in T. So really what's not in part of the union are just these 3 numbers, 1, 5, and 7. So we're going to say E union T is equal to 2, 4, I missed 3. Let's keep them in order. 2, 3, 4, 6, 8, 9, and 10. Right? We just left off these three. So the union in this case is a much bigger set than the intersection was. Let's do the same thing we did before with the attribute pieces. And this time, let's let, again, if S is the small attributes and B is the blue, let's find S union B. Pause the video, try this one on your own, then come back. Okay. If you did that, hopefully what you came up with was a drawing or an arrangement that looked like this. And what you'll notice here, again, notice how it's shaded, right? Notice how all of these pieces are shaded. This is a much larger set. And so rather than me writing all these, I'm just going to copy and paste so we can, again, see what set notation would look like. Set notation would look like this. I think Grammarly is the problem on my computer. Every time Grammarly pops up, it's causing things to slow down. I'm gonna have to turn that off. So let's enlarge you and again wait for the computer to come back. I can disable this right now. Quit Grammarly. There. Much better. Okay. So eliminate that, and there we go. And so this is the set notation, S union B, small yellow circle, small yellow hexagon, et cetera, et cetera. You can see that there. So the union in that case is quite a bit larger. So let's do the same thing we did before again with the follow-up exercise, where we're going to shade just small sections. Okay, so just like before, the first one that we're going to do is the large pieces and the hexagons. Okay, so I want you to sketch out one of those small little Venn diagrams and shade in the appropriate spots. For the second one, we will do small triangles, union small circles. And for the third one, we will do small squares, union small pieces. Okay. And so again, you're going to be sketching out these little diagrams. Go ahead and pause, try those just like we did before, and then come back. So for the first one, large pieces, hexagons, large hexagons. You're going to have some pieces that are not inside there, but the shading will be, I'll use a highlighter, the shading will be all of them, right? It'll be the union. So it's like you're combining these two elements or combining these two sets. What would that list be? It would contain a lot. L union H would be, see if I can get all these correct. Large blue triangles, large yellow triangles, large red triangles, large blue squares, large yellow squares, large blue hexagons, large yellow hexagons. Oops. Large yellow hexagons. What's next? Large red hexagons. I told you it's a long list. Large blue circles, large red circles, small blue hexagons, small yellow hexagons, and small red hexagons. That's quite a list, right? That's quite a list if we wrote that out in set notation. For the next one, small triangles, union, small circles. So we make our rectangle first. If you remember from before, these sets had nothing in common. We had small triangles and we had small circles. But if we're going to shade in what they have in common, we're shade, or not what they have in common, but just shade in their union, it's like this, right? We are shading in both of those circles. And that would contain ST union SC would contain the elements, small blue triangles, small yellow triangles, small blue, small red triangles, and then small blue circles, small yellow circles, and small red circles. Okay. And then finally, small squares, union, all small pieces. Again, the start of it looks like the last one did, where we have all of our small pieces in here. And then remember how small squares was a subset? And in the intersection, we only shaded this. Well, now we're shading this. So this is really going to be all of the small pieces, right? So this is going to equal really all of the small pieces. I'm not going to list them all out this time, but I think you're probably getting the point there. All right, so when you start to shade in these Venn diagrams of what parts are represented, they're much different than the unions. So the next thing we'll talk about is when you have operations of three sets. Oh, three, you can have three sets. We saw this in our introductory activity. And when you do operations on three sets, it's kind of like when you have operations on three numbers. Sometimes you actually need to include some parentheses to make sure you do things in the right order. For example, with numbers, 2 plus 3 times 4 is different than 2 plus 3 in parentheses times 4. If you recall from order of operations, if it's listed like this, you would multiply first and do 2 plus 12. 3 times 4 is 12, and 2 plus 4 is 14. Over here, you're grouping the 2 plus 3 together to be 5, and then multiplying 5 times 4 to be 20. So with operations on three sets, you're going to see that we are going to include parentheses so we can see what we actually have to do first. So what I want you to do is make a Venn diagram, large Venn diagram with three circles. And we're going to be doing this same problem about three different or four different times. And so we're really going to be doing three different triple Venn diagrams here. And so our universal set that we're going to be working with to show this universal set is the whole numbers 1 to 30. Whole numbers 1 to 30. Now, what you can probably do is just do this once, and then when we start to look at the intersections and unions, you don't have to redraw the whole thing, but you can just look at different areas of your Venn diagram. So our universal set is the whole numbers 1 to 30. Set E is going to be the even numbers. Set T is multiples of 3. That should look familiar. But now we're going to add another set, set F, and that is going to be multiples of 5. Before you pause the video and start, I'm going to show you how to arrange your Venn diagram. So we're kind of doing this the same way. So I've got a nice triple Venn diagram already prepared that I will paste here. And I will enlarge this so we can see the whole thing as best we can. Even stretched out a little bit. Okay. All right. So let's close that. So what I'm going to do is I'm going to make we have set what did I say? Set E. So we're going to put E here, set T here, and set F here, right? And anywhere outside of that, again, we consider the universal set. So what I want you to do is see if you can do the same thing, arrange all your numbers in the proper locations in that Venn diagram. Pause the video and then come back here. So let me start doing this as well. I'm going to do this right along with you. So again, I'm just going to start with the number 1. I'm going to work my way up. Let's make it so we can see it all. So again, even, multiples of 3, multiples of 5. So 1 belongs out here, 2 in here, 3 down here, 4 up here, 5 down here. Ooh, 6. 6 is a multiple of 2 and 3, so it belongs here. 7 is outside. 8 is an even number. 9 is a multiple of 3. 10 is a multiple of 5, and it's an even number. So we'll go here. 11 is outside. 12 is even and a multiple of 3. 13 is outside. 14 is even. 15 is a multiple of 5. I missed that one. 15 is a multiple of 3 and 5, so it belongs here. 16 is even. 17 belongs neither. 18 is even and a multiple of 3. 19 is outside. 20 is even and a multiple of 5. 21 is a multiple of 3. 22 is even. 23 is outside. 24 is even and a multiple of 4. 25 is a multiple of 5 only. 26 is even. 27 is a multiple of 3. 28 is even. 29 is neither. And 30 is even. It is a multiple of 3, and it is a multiple of 5. So let's double check, make sure that we got all these in the right spots. Yeah, after taking a moment to just double check my own work, I paused my video to just double check. I did get everything in the correct location. That's an easy one to miss occasionally, right? So if we look in each circle, all the even numbers are in this circle. All the multiples of 3 are in this circle. And all the multiples of 5 are in this circle. Okay. So what we're going to do now is look at some different unions and operations on sets, but we're going to do it with all 3. And so the first one we're going to find is, the first one we're going to find is this. We're going to find in parentheses E union T union F. E union T union F. So let's kind of try to figure out what that notation means first of all, because what you'll notice is that I did put a parentheses around the E and the T. So that's where we kind of have to start. That's where we're going to start looking here. Where is E union T? I'm going to use some highlighting and then I'll just erase it after we go further. E union T. Well, unions are all of it, right? Unions are everything in E, all of these, combined with everything in T, which is all of these, right? So it's this whole area shaded. So I'm taking that and making it a union with F, which means I'm also going to include these. So basically, the union of E and T with union of F is all of the numbers that you would see listed inside here. None of these out here, okay? So we're going to do some shading, again, to sort of demonstrate some of these ideas. So let me undo that. I'm going to undo that shading, and we'll do the next one. So the next one we'll do, so this is number one. Number two, we're going to do E intersect T union F. All right. E intersect T union F. So I'll pull up my highlighter again. And you start, right? See if you can do this on your own first. E intersect T union F. Pause it and then come back. So E intersect T is where? E and T are these two circles. And the intersection point would be here. Right? There's our intersection point. Union F. So we're taking the intersection of E and T and we're adding basically everything else that's in F, which includes these, and these. Okay, so it includes all of these different regions. So what's not included? The even numbers that are outside of F and the multiples of 3 that are outside of F. Everything in F, along with this little section up here, is included. So the next one we'll do is number 3. Number 3 will be E union T, in parentheses, intersect F. And then I'll put number 4 up here as well. Give both of these a shot. You can probably guess. This is E intersect T union F. So go ahead and try both of these on your own and then pause and then come back. All right. So E intersect T union F. E intersect T union F. So where's the intersection point between E? I'm sorry, I read the wrong one. E union T intersect F, right here. The union, we did this one before, right? E intersect T is all this stuff. It's E up here, and it's T over here. So that's kind of our starting point, right? We've created like a new set when we do that. Well, now we have to take that and we have to intersect it with F. So it's only going to be the stuff we shaded just now in green. And then what does that have in common with set F? So I'm going to grab a different color here. And I'm going to grab my yellow highlighter. And I'm only going to reshade the ones that are also, better do a different color here. Yellow is not going to show up. Let's try, actually, let me grab like an orange marker here. And it's going to be these, right? It's going to be only these, right? These are the sections. If we were going to shade it all right here, this section right here, shaded in orange, oops, would be in E union T intersect F. We started with E union T, the green shaded area, and then we said, well, where does that intersect with ones in F? So that would only be 10, 15, 20, and 30, right? Those would be the numbers in this set right here, 10, 15, 20, and 30. All right, let me erase those and do our last one. So E intersect T union F. That's the same one I did over here. Oh, I see what I did. Yeah, that should have been intersect. I thought that sounded familiar. gonna cross off you, and you should be intersect. I'm so very sorry. So you probably noticed that when you did that on your own. So we're gonna look at E intersect T intersect F. So if you have to repause and try that one on your own, go ahead and do it. So E intersect T. E intersect T is going to be here. It's where E and T overlap. So now we're going to look at that section and see where it intersects with F. Well, you can probably already kind of see what's going to happen. It is going to be just that region right there. Right? So where the green section intersects with region F or set F. So that would only be the number 30. Only be the number 30. So I hope that you're seeing here when we have three sets and we have to look at their operations, we have to use parentheses, and you might have to do one part before you can go to that next part. All right, so this brings us to our very last main topic of this video. I told you this one would be intense. So our last topic is called complements of sets. So a complement in any situation can really be thought of as what makes up the rest of the group. In fact, that's how I'll just describe it and define it on the page here. So a complement is what makes up the rest of the group, sort of in generic, non-mathematical terms. What makes up the rest of the group? As far as sets goes, is basically the things that are not in the set that we're talking about. All the other sets that are part of the universal sets, the universal set, but not in the particular set that we are talking about. So to use an easy example, let's say the universal set is the whole numbers 1 through 10. Whole numbers 1 through 10. Set A is even numbers. So we would say A is equal to 2, 4, 6, 8, and 10. Now the notation for a complement is, if we want to know the complement of set A, which means what are the rest of the elements that are not in set A, we would say A and then prime. We put a little, almost like an apostrophe, a little tick mark above it. So that is the notation for complement. So when you see this little tick mark right there, that means the complement of A, okay? And so we would say the complement of A would be equal to all the numbers that are in the universal set that are not in A. Really, that's going to be the odd numbers, 1, 3, 5, 7, and 9. So we have A, and we have the complement of A. And really then, if you take a set and its complement and look at the union of those two things, it's the universal set. So any set and its complement is the universal set, okay? So we're just going to really explore this now through a few simple looking diagrams. All right, we could do this also with elements and other things, but we've done a lot with that, and I think that you're probably getting a good handle on it. And so what we're going to do is we are going to just focus on sketching, sketch and shade. All right, so we're going to sketch and shade diagrams to illustrate these different sets that I'm going to state here. So number one will look like this. I'm going to start with a very simple one, and it's going to be A prime, okay? So if we make A, this is really simple. Here's our universal set. If this is set A, where would we shade to represent the complement of A? We would shade all of this area outside of A. So that would be the complement of A. If A is in the circle, A prime is everything that's outside of the circle, but inside the universal set. So what if we do this? What if we have A union B, and I put that in parentheses, and then I put my little complement tick mark outside? Can you figure out what that might look like? So take a second, give it a shot. Think about what that's going to look like. So if we have set A and we have set B, we kind of work from the inside out. If you first think about what A union B would look like, well, A union B, I'm going to shade in yellow. A union B, remember, is all the elements in both of those sets. So there's A union B. The complement of A union B is all of the numbers that are not in there. So it would be everything outside, right? So the green is going to represent the shading that we are looking for to represent this, okay? The complement of A union B would be everything outside there. Maybe I can even, there we go, delete the yellow. Okay, so I'm going to give you a few more to try on your own, and then pause the video, of course, and then come back. So the first one we will do is, I've got 3 more that I'm going to give you. It's going to be, parentheses, A intersect B, the complement of those. Number 4 will be A complement union B complement. And then the 5th one, the final one, will be A complement and then intersect B complement. So try those 3 on your own. Shade them just like I did the other ones. So you may be back, and I'm just going ahead and sketching our generic set A, set B diagrams for each of these. And like I said, I know that these are maybe new to you. If it's hurting your brain a little bit, that's good. That is good. That your brain is working today as you go through these, right? This is just meant to make you all better thinkers, and specifically better mathematical thinkers. So let's go to number 3, A intersect B. If you remember, A intersect B is where A and B overlap. So the complement of that would be everything outside of that, which includes the rest of the universal set, as well as the rest of set B and the rest of set A. We're really just leaving out that middle section. That's what that shaded area would look like. Now let's look at number 4. A, sometimes we even say A prime, right? But the complement of A union the complement of B. Ooh, these start to be a little bit trickier. So the complement of A, all right. So I'm going to start shading in yellow. The complement of A, I'm going to shade in yellow. So A is this circle. So I'm going to shade everything outside of that. Everything outside of A is here. It includes part of B, right? Everything outside of A is that. Now what I'm going to do is I'm going to use, let's use maybe a pen, orange pen. So now let's do everything outside of B. So outside of B is going to be this area all outside in the universal set. Oops, didn't want to do that. undo. Okay. Everything out here in the universal set outside of B. But then also it's going to include this part of A as well. So really what I'm shading here is everything outside of B. All right. What we're looking for now is the union of those things, right? The union of those two things. So again, a union is not where they overlap, but everything that we just shaded. So really, I'm going to shade in my final green everything here, here. This is a beautiful color, right? Everything here, here, all this part of B, everything outside. And all I'm going to leave open is that tiny little wedge in the middle. Do you notice something? Oh, look at that. These are equal sets, aren't they? Notice numbers 3 and 4. Those things, the complement of A intersect B, and the complement of A and the union of the complement of B are actually the same thing. They have the same elements. They are equal sets. And then the last one we'll do is the complement of A intersect the complement of B. So just like before, I'll do the complement of A. So everything outside of A. I'll do this a little faster this time, because we've already seen this a little bit. Complement of A. And then the complement of B, just like before, was everything outside of B. So here, 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 here. And what we're looking for is now the intersection, the intersection of those things, right? Where did we highlight things and they overlap? Where did we both color in yellow highlighter and orange marker? Well, that's going to be this area. This is a little harder to show, right? It's going to be all this area outside of both circles, right? Everything in the universal set that's outside of both circles. Right? So if you start to examine this in a little more detail, what you'll notice is this section right in here only has yellow. This has nothing, and this only has orange. So maybe I can even clear this up by going boop and boop. Look at that. There is our, there's our intersection. And did you also notice that was the same as number 2 up here? So again, we have equal sets shown in very different ways. And so the last thing I'm going to have you do is kind of work those backwards. What I'll do is I'm going to put out the different shaded regions, and your job is going to be to determine what the set notation might look like for each of those. So I'm going to do 4 different shaded regions. Copy and paste these. And your job again is to determine, analyze these, and see if you can come up with some set notation that shows, that represents what these shaded regions are. All right. So again, pause this video and then come back. Okay. So hopefully you've had a little time to try to play with these a little bit. So if we examine this first one, we'll call this number 1. Number 1, what I notice about this is that everything is shaded except A. Anything in set A. Nothing is shaded in set A. So how would we describe this set that's shaded? I would say, let's describe it as just A prime. It's the complement of A. Everything outside of A has been shaded. Okay. Let's go over to this one. This one's got a lot going on. All right. So One thing that you might have noticed is that everything inside set A is shaded, right? So we know everything inside. This might take us a couple attempts to kind of work through to get here. So everything inside set A is shaded. But then we've got this extra little piece here, right? We've got this extra little piece right in there. So how do we take everything in set A and add it to this? Well, we do it with a union, right? We are going to take set A and we are going to union it to something else, okay? So we have to figure out how to make a union of set A with this thing. Well, how could we, if we just focused on this piece, is there a way we could describe it? That's a little tricky. So what we might want to do is expand it to this entire wedge that looks like a little football. This one's a little bit easier to notice. Do you see this shaded region right there? Can you come up with a way to describe that using the sets? That would be sets B and C, but the intersection, right? That right there is B and C, the intersection of them, just where they overlap. So what we're going to do is take set A and take the union of it with B intersect C. There's B intersect C, and then we take the union of that with A, and we have our shaded region. That one was a lot tougher. And then our third and final one. So what do you notice here? So what I notice is that, first of all, it's everything that's outside of A except for this little piece right there, right? So it's kind of like we have to start, maybe, I'm going to start with everything outside of A. So everything outside of A is the complement of A. Well, that takes care of all the shaded region except this, correct? So what would be a way that we could include this little wedge to what we already have? Well, one way is to make a union, because that just sort of adds on additional sections, anything that is in set B. We already included a lot of set B, but we hadn't included this little piece yet. So all we need to do is take A prime, or the complement of A, and union it with B. And there we go. So these are certainly challenging, right? And this is going to take, it's going to take a bit of practice. It's going to take a bit of practice. You might even have to go back and rewatch parts of this video. Make sure to read the text through this as well. But this really does get to the heart of these operations with our sets.